Welcome back to the stream. Happy Friday. Gosh, this water bottle's noisy. I need a different thing to use while I'm streaming. Yeah, I can like choose to make a variety of different terrible noises with it, but I don't know that I can use this quietly. Maybe I just take off the non-spill lid and then inevitably spill it everywhere. It's at least shorter and unpleasant. Anyway, today's stream is going to be some kind of low-level troubleshooting and debugging and weirdness inside of Grub on this kind of weird old 486 industrial PC board. Tuco's outside, but I'm sure he'll be back here at some point soon. Yeah, so we've got a bit of an overhead view here now. Does this have the camera on it? Yes. There's the actual whole setup right now. It's a bit of a mess. This is the circuit board and screen that would normally be inside of a suitcase-shaped contraption. And a front panel over there, and a smart card reader, and a thermal printer. The only modifications I've made to this so far are to break out some additional I/O. So I've got a logic analyzer connected to the ISA bus. And I've got one of the serial ports connected to a USB to serial adapter down here, which I've been connecting to the Raspberry Pi or to this desktop Linux machine. And 2 goes back. Hey, boy. Yeah, something like that. Oops. He might just demand that I open the door back up. Anyway, I've been trying to debug this rather strange boot up problem where I can get into Grub and somewhere fairly late in the boot process of trying to boot Linux with Grub, it just crashes. And at this point I can narrow it down to something within or past this relocation process, which is where Grub moves some of its temporary memory into new locations, in this case kind of low memory in the sort of DOS 640K region, and then eventually prepares the execution environment for the next operating system, whether it be 16-bit or 32-bit, and sets up the CPU registers and actually transfers control into the operating system you're booting. So I don't know how far into that it's actually getting. When I just try to boot Linux normally, it just hangs before I actually see the decompressing kernel messages. It does seem to be actually reading the entire kernel into memory successfully, but not decompressing it or running it. If I tell Grub to do like a SHA hash of the kernel, it comes back fine. So like Grub is reading the disk just fine and loading things into memory from the disk just fine. Take what you want. And so I tried a couple different OS boot scenarios. I tried loading very simple images that didn't have any external dependencies, and those were also failing. So the simplest test I came up with was to just tell Grub to use the chain loader to just load the MBR that I just booted off of, which should just create a loop. I should just be booting Grub again if it works successfully, but instead it's crashing, and so I'm trying to debug why that part is crashing. And it's been weird. The last stream I spent mostly dealing with running GDB on Grub to try to step through the code and try to figure out where it's crashing there. And that came back honestly kind of inconclusive. So this is like roughly the test setup we've got here. Oh, to go. I've got this Docker setup that I've been using to build the disk images, and then I can run them either under QEMU or on the real machine. And I got QEMU set up here to use the same serial port settings as the real debug port that I've got this connected to. I don't know if Tuco actually wants the door open or if he wants to stay warm. Those two things are slightly at odds right now. Yeah, so I thought one actually interesting kind of quick thing I could do with this setup now that it's in this state is I could try reproducing the test from yesterday where I used GDB to step through the relocator's memory copy and just kind of see how far that gets. Because I know it's crashing there when I use the GDB stub. I don't know if that's actually where the crash is or if that's just an artifact of the serial debugging that I'm using. I have no reason to believe that that memory should be necessary for the debugger to operate. So it could be the real crash, or that could just be an artifact of something else that's going on. I checked into some of these memory regions, and it looks like everything that the debugger needs is up in this high memory area above a megabyte where the module for the debugger loads, and this is the GDB support module for Grub, which is actually probably included on your copy of Grub. If you just did like GDB stub on your Grub prompt, it would probably dump you into a attachment for a debugger. So that's the functionality I've been using here. Really the only modification here is that I've got this Docker image set up to build Grub from source, and I'm copying out this build tree, which is full of delicious symbols and prepared debug scripts, and we can use this outside the machine here to just get our GDB configured just right to attach to Grub, running on either the real machine or on QEMU and debug it. So then I just got this QEMU set up. It would be cool actually to try using the serial port over TCP also, because it's a little physically easier to connect that to the Raspberry Pi instead of going through the KVM switch again, where if Tuco leans on it wrong, I lose my serial connection. Alright, well, Tuco's gonna be all cat over there. Yeah, I don't know if anybody wants me to actually, like, explain any of this. I've been mostly not explaining things except, like, in bits and pieces, but it's also probably pretty easy to follow. I don't know. Also, probably people don't care. I've still got to figure out which parts of this are worth using in, like, condensed videos, if any. Anyway, I think that's fine. We can just try running this. So I've already got that built. If we just run this, all that's still in the Docker cache, but we can grab bits and pieces out of it. then I want to run the emulator and then attach Grub to it separately here. Cool, so this should just default. There's a timeout that's cut off because my font's too big. It had a 5-second timeout, and then this is running just like it does on the real hardware. It's waiting for me to attach the debugger. Cool. And so that ran a GDB script, which loaded some extensions for dealing with Grub loadable modules. And it gave me the symbols for the Grub kernel, which is the initial program that it contains like the rescue mode console, and it also contains the actual dynamic loader itself. So one thing we were doing previously was to follow the linked list here in Grub DL head. So this is actually a pointer to these structures that have information about each loadable module, or each module that's been loaded. And you can follow this. And so I was using the GDB add symbol file command. But this set of macros for GDB has a handy, what is it called? Load all modules. We'll just walk that linked list and load all of the files for me. So then we should have full symbols for everything. And so in this case, everything's running on the same Linux machine. There's just one modern Linux desktop, which is running an emulation of the 486 with the entire disk image that I built in Docker. And then it's also running just a regular modern local architecture GDB, which knows how to deal with 32-bit x86 code also, and loading symbols out of these regular ELF files. So it's all pretty nice. I mean, a lot of Grub's philosophy is that like bootloaders shouldn't be so weird. People should use regular OS ELF files for more things. So it's really not surprising that you can use like completely regular debug tools to debug ELF for the most part. So part of the point of this experiment is I don't know really how far that goes. Like, I was hitting this limit where during that last boot up stage, that relocator that tries to move things around in memory, I was crashing with the debugger attached. And at this point, I don't know whether that is the actual thing that I'm trying to find, whether that's the actual crash I'm looking for, or whether that's a problem that is just specific to the debug setup. So I'm trying to reproduce this in an emulator, and the emulator does not have the crash that I'm actually looking for. I can just boot Linux successfully in the emulator. So whatever the difference is between the emulator and the real hardware could point to this problem I'm trying to find. Okay, so now I've got these two windows which are both ready to go. Gosh, it'd be cool if I could get everything to fit on the screen. Yeah, that's fine. Happy Friday, by the way. Alright, well, I want to load some more modules, so I should let this continue for a minute. Okay, so that automatically loaded the symbols for modules as they were requested. It's all very convenient. This script is pretty straightforward too. We looked at the source just really briefly on the last stream. And also just tried doing this fairly manually. I think the script is a bit more careful about loading all the individual segments. I was making assumptions that the relationship between segments was preserved by the loader, and so maybe that's not actually the case. So maybe when I was loading them manually, I was only actually getting the code addresses, like the text segment, right, and maybe the data segment addresses weren't loading right. But they should be loaded all right now. So I think we want relocator 16 boot. Cool. I think I had some extra keys in the buffer, which is what dumped out a bunch of stuff. So that'll give us a debugger trap as soon as we enter that last stage of boot up, which we can trigger by typing boot now. Okay. So this is just the end of this function. It was preparing lists of these memory areas and writing code to deal with that. So I think what we've got now is we've got a chunk of physical memory. Ooh. That is very different. That's a very different address than we had on the physical machine. Okay, so that's one thing. On the physical machine, this got allocated right at the 1 megabyte boundary, and this is way up there now. Gosh, what is this? Yeah, okay, this is like in the vicinity of 128 megs. Really? How much memory does this VM have? I didn't actually set the amount of memory, so maybe this is near the top of RAM. You know what, before I get too deep in this, I'm going to tell QEMU to simulate a machine with 32 megs of RAM, just to make this make a slight bit more sense. Oops. Oh gosh, and part of me wonders if I could get away with telling QEMU to boot the exact BIOS image I've got. That would make debugging interesting, wouldn't it? I don't know how far that would get. That would really depend on the video BIOS failing gracefully. And I know the BIOS does a bunch of stuff to the chipset registers, but I think a lot of that stuff might just be able to fail silently. Yeah, that might be interesting. Should we just try that? That feels like a tangent, though. I don't know if we'd actually learn much from debugging the BIOS in QEMU. M gets a nice short option. -M32. Should we try to just load that BIOS? I don't think it'll work, at least not without a lot of effort. But I'm curious how it fails. Oops. Just dash BIOS. Here goes nothing. I mean, it's crashing somewhere. That's all we know now. There's a whole rabbit hole we could go into trying to debug this, but it's probably crashing on one of those many early initialization steps that depend on like detailed knowledge about the motherboard. So yeah, maybe some other time. Oh, we are experiencing some lawn care in the local vicinity. Sorry about that. Okay, where to? Chain loader. Back to the debugger. And then breakpoint in the relocator. Oh, that first breakpoint was created for the dynamic library loading. All right, continue that. Boot. Go down a bit. Okay. Okay, well this is still a very different address. We're using an address near the top of RAM still, so it's no longer near 128 meg, it's near 32 meg now. But yeah, so on the real system, this was using probably the lowest address that it could. And now it's probably among the highest. I don't know if that has a difference, or if that difference is just related to like the BIOS memory tables. I forget what form of that, this system would have. There have been a bunch of different ways over the years for the sort of system firmware to pass information to the operating system about what memory regions are special in what ways. And it's certainly possible the BIOS is doing something very strange here. I'm sure Grub has a command to debug that, right? There's a question about what it would have been useful for to set the BIOS. I was trying to get QEMU to use a BIOS that I dumped off of this actual board instead of the built-in BIOS. So it's like a compatibility nightmare, right? Because the BIOS has a lot of very detailed dependencies on the actual hardware on the motherboard. But if it were to work, which it doesn't yet, but it could with some effort, if I got it working, it could be a way to debug anything that I think this BIOS is doing strangely. So, like, for example, if there's a bug in the way the BIOS is describing memory, or if there's some like non-standard feature in the BIOS, or if I want to try making a modification to the BIOS to add some feature that's missing, then having that BIOS work in an emulator would give me a really powerful tool for doing that debugging and or development and or modification. I should finish stepping through this. There's a lot of interesting avenues to explore at this stage. Oh, wait a minute. Is this the problem with the local variable state in the debugger? Because relst is supposed to be just a short distance away from that, at least if I'm understanding this right. Okay, I might just be misunderstanding this code because this is definitely using both memory areas. Maybe it allocated up first here, or maybe this value is irrelevant. But relst, which is the pointer it's about to call, is in about the same location we were seeing. So that's actually the same. I think what's going on here is that at the 1 megabyte mark, there are a bunch of little snippets of code that are used to get the system set up to run the actual 16-bit mode operating system that we're chaining to. But then right above that, there are some bits of code that are basically just like little kind of purpose-coded mem copies that grab chunks of memory from the kind of temporary high memory locations and move them down to locations that may otherwise be occupied by like parts of Grub, or I think that's mainly what we're avoiding here, is we're trying to be able to have a fairly full-featured sort of operating environment in Grub that they can use for making decisions about what to put where and what to load and like getting the memory contents ready, and then have a very simple piece of code which has to be the thing that is carefully written not to overwrite itself, and that's the relocator. So far this is good. Let's see how much further we get. So now we're at that address. And this is the same memory copy we were seeing before, basically. So it's writing to... Is that even writing slightly to a different address? It's the same vicinity, though, like around 8,000 hex. So this is copying that 16-bit portion of the relocator to an even lower address. It's copying it from right at the 1 megabyte boundary to well below a megabyte down here at, what is that, 16K? So at this point, the way I was debugging this was just to try single-stepping really quickly and watch where it crashes, which is annoying, but not that annoying. Oh gosh, this is slower in the emulated system than it was on the real system. On the real system, the limiting factor was all the serial port I/O going back and forth. The emulated system doesn't have the serial port speed limitation, but now I think it's just slow because it's emulated. Just gonna fill up this buffer. Fill up the buffer, pet the cat. I guess it might be worth taking the same approach I did before, where I maybe assume it will make it through and set a breakpoint afterwards, since it is pretty tedious to step through byte by byte. I guess that isn't actually the same test, though, because the thing that I do want to know is, will it break if I'm single-stepping in the GDB stub? Going through with a breakpoint at the end is not actually the same operation. Sometimes science is tedious. GDB stubs are fun, though. If you ever find yourself in a very minimal environment, it's probably still pretty easy to get a debugger attached to it. The GDB stubs only really need to know how to do a few things. Was that it? 828A. That sounds familiar. What did our notes say? A. Yeah, that points pretty strongly to this just being something which is vital for the debugger to operate in a way that I don't understand currently, because we're getting the exact same crash in QEMU. So that is a great data point, and that makes that segues pretty nicely into the next thing I thought we could try. Yeah, so crash there. We could now actually debug this crash, because now that this crash is reproducible in QEMU, we could actually attach a debugger. So here QEMU is emulating the debug stub that Grub is using, but running this in an emulator, you have the additional option of attaching GDB to the emulator itself. So I could debug the crash in the Grub debug stub using the QEMU debug stub. I don't think we need to do that, though. I think I'm just going to accept that this is why it's breaking. So, I think the next thing I want to try is not using the GDB stub and debugging this. So as handy as the GDB stub is, I think I need a way of getting deeper into where this is crashing without having really any dependencies. Yeah, I mean, I'm no expert in this code that I'm debugging, obviously, but it seems like it's written such that it internally needs pretty much zero dependencies on external memory. It just uses its own little self-contained chunk of code. So I feel pretty compelled to just follow in that path and just add a little tiny self-contained thing that debugs using I/O ports. Yeah, embedded systems are a lot of debugging the debugger in my experience. Alright, so there's a bunch of different options for this, especially since we've got this logic analyzer. It might make the most sense just to do basically serial port printf debugging. except that in the innermost parts of this code, instead of actually doing like a regular printf, we could write directly to the serial I/O ports so that that code can be self-contained. So that'll be a slightly different setup here. So here we'll reset this and not let it go into the debug stub. And then that should be connected to the serial port in here. There's not a single command to set both the terminal input and output, is there? Uh-huh. Right. I guess I could have done those both on the same line. I was just getting used to how GDB doesn't let you combine commands with a semicolon. Okay, so now we're connected over an emulated serial port. So we can do set debug all to get all these extra messages, and then same experiment. Chain loader. So most of that was it loading, well, I guess there were a couple big things. There was it loading the modules in the chain loader itself, and then doing a bunch of file system related stuff to open the thing that I asked for, which was actually just the first block of the hard disk. Oops. So now let's just see how many debug messages we get and if it actually boots. Okay, so in this case it did actually boot. So we chain loaded successfully. We didn't actually hit the crash that I was trying to debug because QEMU works and it boots things. This is the last normal debug output we see. So this is actually identical, as far as I can tell, between this and the physical machine here. This is from some C code that is preparing the inputs to that relocator, but then the relocator itself doesn't have any output because it doesn't have access to the printf routines. So I think the only change that I need to make here to get the output that I need, or the information that I want, is to just add some really low-level serial port output to the relocator code, like in the vicinity of those mem copies, and then I can test it in QEMU to verify that the debug code works, and then copy this disk image to the real machine, and then see where it crashes. So I'll be right back. Let me leave you with Tuco for just a moment. cozy. Gosh, the really low budget version of this debug output would just be to splat a character to the screen for each mem copy and then modify the C side of the program to make the mem copies smaller. So I think the thing to do now is to develop a patch for Grub in a local tree, and then stick that into this build system to get it into our disk image. Excuse me. Let's make sure this compiles. Yeah, I already had that compiling outside the Docker. Man, basically all of Grub is in this Grub core directory, even the modules. Name doesn't make a ton of sense to me. Relocator asm. There's relocator common, which is an assembly file, There's relocator 16, 32, and 64, which are assembly files. There's relocator, which is a C file. And then there's relocator asm, which is an assembly file. Oh gosh. Anyway. Chunk size. So, like, the most straightforward way that's coming to me is to add some code after each copy, because then I can reuse some of the registers that were destroyed in the copy. Otherwise, I'd have to save registers. Yeah, I don't know. I guess I don't think I even care about outputting any of the contents. I think I just care about outputting some progress marker. Yeah, so maybe I'll just have it output like an F for every forward relocation and a B for every backward relocation or something like that. I can do it at the beginning, I guess. I could actually do a character at the beginning and at the end. So then it would at least narrow down to, you know, definitely being inside of a single copy. And then once I have that, I can modify the C code to move the copies around if I want. So, and what registers can we use? It looks like AX, CX, SI, DI. I need DX to do IO, right? I might have to look at the context here to see if it's okay to trash DX. Actually, is there a way to do IO without DX? Now I'm curious. Only if the port is 8 bits, which it isn't. The serial port starts at 3E8. And I do need to read the, I forget what it's called, but there's like a status port that I can read to see if the FIFO has any room before I write to it. Can I trash DX? I mean, normally you'd be able to save it to the stack or something, but I could just save it to SI or something weird like that. Fine. I don't want to like make any changes to the environment that I don't have to, so saving and restoring a register is preferable to trashing it. And we are in AT&T syntax land. Oh gosh, syntax. So what are we even doing here? We first need to save DX. Do I need a... character for immediates here? I forgot. Yeah. Dollar. Right. Oh, the assemblers do this differently. So 3. That's right. So first we need to deal with the flow control. Oh, this is like the worst 16550 summary. Like, thanks for trying, but yikes. I seem to remember Wikipedia linking to an actually okay one. We want this bit. Line status register, offset 5, bit 5, empty transmitter holding register. We want to just busy wait reading this register until this bit is set so that we don't transmit bytes faster than the serial port can actually send them. And this won't have any memory dependencies. It'll just use a couple of registers that we were going to use anyway and some local jumps. And that's offset 5. I can just ignore the upper half of this, right? I can just write to dx and just not even worry about the upper half. Oh, how do I do local labels in GNU assembler? These labels local by default or something? That couldn't be right. I'll cross that bridge once I trip over it. was 20, right? Yeah. Gosh, I need to turn off that autocomplete. It's only ever completing stuff when I don't want it to. Probably want to make this a macro, right? I mean, just for debugging purposes, I don't mind copy pasta, but this would really be a macro under any actual circumstances. Tuco. Let's see if that assembles or like where the errors are. Okay, what if we just put all this up here? Gosh, that key combination is uncomfortable on this keyboard. Something kind of like that. Does it macro? Ooh, does it macro? So there's a little chunk of assembly code we're adding before and after each of these suspicious mem copies. Hugo is super cute right now, huh? Who did it fail? Oh, yes. Good job, linker, catching that undefined symbol. This looks like it's gonna work. I should just package up this patch. Yeah, okay, so that builds fine on my local machine here, or on my host machine, I guess. Now I'm actually going to stick it in that Docker build system so that I get an image that will work on this 486. So mainly something that is 386 and has a disk image of the right shape. Okay, the patch applies. So now I get to compile Grub. so much compiling. Cool, so now we can try the same experiment and hopefully get more debug output. Oh, that's right, we don't want the remote debugger for this. So command line and then terminal. That hopefully works. Yeah. Okay, so that is our emulated serial port. That's different from what I expected. Oh, I should have also turned on that other serial debug option. So I get 6 lowercase b's. Alright, why didn't I get any uppercase b's? I should test whether my serial port flow control is working, because that could cause all sorts of things to not show up right. Like we could just be dropping characters. Can I disassemble this code to make sure it looks right? It's always nice to disassemble stuff that you assemble using a macro. This is in the relocator module. Looks right. I don't know how that would fail. Lost my physical serial port wire again. Let's just try that again and see if there's any variability to the output, and also take the opportunity to turn on the rest of the debug. Okay, just interrupted the timer there. So here we get a bunch of the kind of unrelated debug output, and then the C portion of the relocator gives us that sorted chunk list as the last thing here. You know, actually it looks like we only have 3 chunks, so I would expect there to be 6 characters. It's just I'm not getting the capital B's. Did I just not capitalize this? I capitalized it there. Oh, I forgot to actually make this take an argument. That would do it. Cool. That's a nice, tidy explanation. I need to fix that up here. Just make sure that fix compiles. don't actually know how macro arguments work. How does macro argument works? Percent. Really? That doesn't look right. Backslash. Gosh, okay. Man, GNU assembler, why are you so like that? Oh, there's some folks in chat who probably want some context. I'm still trying to debug why this machine doesn't boot. I've got it booting Grub, but nothing past that. And on the last stream, we did some serial port debugging of Grub itself, but we got into a pretty low-level portion of Grub that we actually can't debug with the serial port debugger because it crashes. So I'm trying to write some lower-level serial port printf debugging to see how far into that section we're getting before we crash. And the specific thing I'm doing right now is recompiling Grub with a patch that adds some low-level serial port output. Alright, the patch applied. Now we've just got to compile Grub again. Good kitty. Okay, that'll compile for a minute. It looks like this is basically working on the emulation then. So I think once that bug is fixed, this is going to turn into capital B, lowercase b, capital B, lowercase b, capital lowercase. So we'll have 3 copies, all backwards, and they all succeed. So then I can just compare this to what happens on physical hardware and see what's different. Let's start up Minicom. Cool. So while this is compiling, I should make sure that the serial port is all still wired up by just giving that a quick test. Cool, so now same situation, but real hardware rather than emulated. So if I run this without the debug output that's still compiling, I get this same sorted chunk list here, and then the machine is crashed. Might be useful to actually take a look at this crash on the oscilloscope also, just see what the bus is doing in the vicinity of it. Okay, Grub's compiled. This is just assembling the image. I should get the CF card reader ready for it. And this is part of the build process that installs the bootloader, so it installs Grub inside of QEMU. Is crashed. I guess it would have been useful to send a more unique character to the serial port so I could use that as a scope trigger. I don't know, I'm not seeing a lot of capital B's in there. I could probably do a segmented capture at least. These cards are so slow. real serial port. Okay. Ooh, forward copies. Interesting. And they all succeeded. Interesting, right? So what's next, and how can we debug that? Well, cool. Let's maybe just try to trigger the scope on this. That's interesting, right? I haven't looked at the code that chooses whether to use the forward or the backwards copies. This is for like memmove style, where if the memory is overlapping, then it matters which direction you move across it as you copy. So it supports both. I haven't seen it use any overlapping memory regions though, so it doesn't seem like it would matter, but it's one of the differences between this and the emulator. Alright, what should we trigger on? We can get serial triggering, right? How am I going to have to convert this? I'm just going to try triggering on a capital F to start with. I don't actually remember which direction this is set up. I think that's the right direction. Let's see if it triggers if I set it as TX. No. Oh, wrong keyboard. Oh wait, so that would be RX. Sure. Oh. Okay, so I can, that's me triggering on just sending out the capital F, so then I'll switch directions and switch the mode so that we just trigger on the incoming ones. Okay. Sure. Okay. Huh. Whoa, that's new. Oh, it just turned off. Yeah. Rescue mode. How did we get here? Is there something wrong with my card now? Yeah, Grub is failing to load now. Gosh. Should I read this card back in and see if it's been damaged? Depending on like in what way it's crashing, it's certainly possible that it could have written to the disk just then. Be cool if I had more than one usable card for this right now. That's a bad sign. Okay, what changed here? Right? I mean, this worked once, and now it's not working. I don't know what gives. Okay, I don't think that should make any difference because the card wasn't actually different. To go. Yeah, it's in the Grub rescue shell. Why? Grub rescue shell is going to be a pain to deal with because the watchdog timer is not disabled. Attempt to read or write outside of disk. I wonder if I lost my BIOS settings. That would do this. I bet this is the failure mode you get if the CMOS memory is trashed. I did need a non-default setting for the disk geometry here. Oh, come on. And I've got to beat the watchdog timer through all of this. Oh, it looks like somebody in chat had the same thought that I did about the BIOS config. Yeah, gosh, that's totally what happened. This needs to be 11. Gosh. Gotta remember that a vital piece of this computer's configuration is stored in RAM, that the BIOS could corrupt at any time, and it depends on a pair of AA batteries. Oh, and it just turned itself off, so I'm going to need to reboot it manually. Yay. Gosh, okay, that was it. Much better. So watchdog timer is fine now. Yay. Oh. Except I need to type that again. That's better. Gosh, button. Oh. So this is going to be something probably in the very end of the relocator, like, is this something related to the CPU architecture? same thing here. I wonder if it corrupts the CMOS memory every time. Okay, didn't corrupt it that time. I should add an option to that menu for serial console. Can you put multiple words in there? Pretty sure. Really? That's weird. I don't know why we don't have the config file man page. I guess it likes single quotes. So, the relocator. Relocator jumper. Gosh, I was trying to get a scope trace. The scope's only got one segment. I should see why I didn't grab more than that. Maybe I just had the wrong time base. Yeah, let's maybe not do a segmented capture. This is looking a little better. Okay, I'm not going to update the card just for that, but it'll be here next time for slightly more convenience. Let's go back to the serial port and try to get this on the scope. Microseconds. Okay. Empty grub shell. Just switching the terminal. Will this trigger on F? Let's try that. Just adjusting the scope before I do this for real. Okay, so there's a view of just pressing F on my terminal, and then the scope is triggering on the F that's coming back in the echo. And how much detail can I see? I can see the individual I/O cycles on the bus still from that distance. Let's try that. Out out of memory. Huh. Was that just from running the chain loader command multiple times? That's interesting. Okay, that's actually not the failure I wanted, but let's reboot. Sometimes it powered on and doesn't actually power on. Okay. Let's turn everything off before it rewrites its entire ROM. So this was that last line of debug, that sorted chunk line. Ending in OX40. And then there's the first F, which indicates the beginning of one of these mem copies. And we have that mem copy ending, and then the other two mem copies are two? Yeah. That's the last of our serial output. Lots of I/O though. And then a bunch of nothing. That section where the bus is stuck on O3ED for a long while, that shows us exactly where the little loop we added is polling for space in the transmit buffer. So there's a little bit of a delay between where we actually see the serial byte come out and where it gets put into the buffer. I think this little blip right here might be where that last lowercase f goes out. And we got the 3Ds. Those two. next on the I/O bus? Hey, what's next with these addresses? That is 80, which is a historical kind of debug output port. So it also might be used as a delay here. So that's interesting. It probably shows up in the Grub code at some point. What are these? I feel like I should know what these are. Yeah, ET 70 and 71. 70 and 71 are for CMOS RAM. And I don't know what ED is. It's not documented in this list from Box. Yeah, I'm wondering if we're already in BIOS code. Like, it's possible that some jump or some memory preparation in Grub failed and caused us to re-enter the BIOS in some kind of haphazard way here. You know, if we were executing code from BIOS, I think we'd be able to see that on the address bus. Yeah, I'd have to zoom in a little more. I'm going to redo this experiment, but get a higher resolution trace. This view really needs the overhead camera, huh? Can we add this without crashing OBS? It's better than nothing, I guess. Okay, same thing here. Got those 3 mem copies. One, two, three. So this is a shared address bus that's going to be used by a few different pieces of hardware, including the video controller, all the legacy I/O peripherals on the ISA bus, and the system BIOS ROM, which we are executing code directly out of when we run BIOS code. So I don't know what these different addresses are, but some of these might be... I mean, I wouldn't be expecting Grub to be going into the BIOS super often here, but if we're writing to the screen, some of these might be graphics related. All right, we could check hypotheses about this being BIOS code by taking these addresses, and there'd be several places we'd have to check because we don't know the high bits of the address, but because we know most of the address bits, we could look in a few different places and see if there's a corresponding I/O instruction in the BIOS code. Right, so this is after the memcopy. I haven't looked to see exactly where we're trying to jump here, but I wanted to see what the context was for, or was, as far as like what the machine is doing on the oscope here. And so right after we see that last lowercase f go out from that last memcopy, we're getting a few other I/O ports. I saw one right to that post debug port, OX80, and now there's some stuff that looks like I don't expect that like Grub itself would do this. This seems like something that BIOS would do because it's accessing CMOS memory and this port ED, which I think is something board specific. It has 20, 21, 70, and 71. 70 and 71 are CMOS RAM. 20 and 21 are the programmable interrupt controller. I think AO and AO1 is the other programmable interrupt controller. Yes. And then F1. This list has F1 down as a math coprocessor reset, which doesn't make sense in this context, so I'm guessing it's something board specific. And this is more stuff that could represent executing code out of ROM, like somewhat sequential addresses in this zone. This is more of the same, more debug post writes and more CMOS and more pick. Oh, 68. 68. This doesn't seem meaningful. This just has a note about something for a turbo mode. This is probably something chip specific. Oh, 60 is the keyboard controller output buffer. This is looking a lot like early post, like we just probably entered BIOS somehow, and now BIOS is trying to post and it's going to fail. And so maybe it cleared memory, or maybe it cleared CMOS because it had a post failure. Yeah, lots of keyboard controller and debug port here. I wonder if it's like polling for keys to enter the BIOS menu at this point. Six, 8. We already saw that one, right? Yeah, I don't know what 6.8 is. More interrupt controller. More post debug. Yeah. I'm a little curious where this starts to fail though. This still looks like basically normal post. We have 3D4 there. What is that? That's like an I/O port, right? I mean, not just an ISA I/O port, but like, oh, that's graphics. That is a legacy CGA CRT controller. So BIOS is starting to set up the display. Are we in video BIOS maybe? I wonder if the BIOS uses that ED as a delay port. Four threes. This is timers. Okay, this is interesting. Now we've got these regularly spaced outputs, which seem to be debug outputs, like maybe it's doing something and might time out and giving us some progress on the way. There's some single ones here. What is this? That's also ED. This. There's a question from chat about whether I can save this stuff to a file. I mean, yeah, there's a whole other logic analyzer I have connected slightly differently that I can use for that kind of thing. But I'm actually a lot more interested in like kind of taking in the context here rather than just focusing on like, the list of operations. Also, like there really isn't a single list of what I/O ports do what on PCs. Like I've got this list here which comes from the Box project, which is a PC emulator, and it has a lot of things on it, but like it doesn't tell me anything about the ports that are specific to this board, which is a lot of what I'm dealing with. So presumably there was some timeout that happened and then it failed and like something else is happening now. These might just be like their interrupt, save, and restore routine, so we're seeing a lot of the same pattern. Alright, finishing up with a postcode. So that's probably the BIOS trying to crash. So the last thing we see it do is writing a value to the debug post register. And there are a bunch of ways to debug this. I don't have access to the data bus on this oscilloscope, but if we did a trace with the other logic analyzer and got the same byte, we could figure out what byte it's writing. Because I do have the addresses, I think we've got information about where in the BIOS it was actually running code when it crashed. So we could probably trace these addresses down to the actual out instruction that generated this. And we wouldn't know what the code was that was going to out, but knowing where the instruction was is probably all you need. So that's interesting. The thing that I'm more interested in right now, though, is how we make the transition from Grub to the BIOS, because that's what Doesn't seem like it should be happening. Okay, this OX80 is the first I/O that we're seeing after that last F, and I'm pretty sure this would be coming from the BIOS, so maybe we can work backwards and see when the address patterns change significantly. I'm guessing this is already in the BIOS at this point. '22 and '23 are the indexed system-specific registers, right? Yeah, I was just referring back to my old code for this. So 22 and 23 are the registers that have all of the system-on-chip specific configuration. So you would definitely not expect to see those in Grub, but they'd be all over the BIOS, especially at the very beginning of code execution in the BIOS. This camera too warm. Give that camera a minute to cool off. Yeah, so these are going to be register reads. Because I don't. Oh, you know what? I don't get external read or write pulses for these because they're actually masked off by the chip's internal logic. So I think these registers always are sort of handled internally without going out to the external bus. But there's no gating on the address bus, so if the CPU spends time with its address bus pointed to that value, even if there's no external write strobe or read strobe, we can see that on the scope just from looking at the timing. It's annoying that the scope doesn't update the byte display in real time, like only when you pause scrolling. Ooh. That is a reboot. Right? 7FF0 is the processor's reset vector. Oh, hey Tuco, you're so loud now. Talky boy. Hey. You just want all the attention? How can I get Tuco on camera? Oh. Oh, are you just gonna try to chomp on that entire thing? Now Tuco's interested in the tripod. Hey Tuco. Breaking, what is this, all the walls except for the fourth wall? Breaking walls 1 through 3. Tuco, why don't you stand somewhere where there's a camera? I mean, I guess I could try the camera that's been overheating. Oh, don't claw at the screen, gosh. Honey. Tuco, what do you want? I kind of want to get an even higher resolution trace now that we know there's a reboot. So I can trigger the scope on the reset vector. Oh, Tuco. You're purring. Why so purry? Oh, I should turn off the base cut filter. Let's try. A little bit more low end. set this up with one hand while I hold the mic with the other. Should I just give Tuco a mic to keep? All right, Tuco and I can both have a microphone. There's a theory that Tuco is just sleeping so much because he's bored. Why not both? He sleeps a lot. He's also got quite a lot of energy. Yeah, he's just completely laying on the mic now. Not gonna bother with this debug. I don't think we need any of that anymore. Why no trigger? Oh. That's the problem. I was telling it to trigger on I/O. Yeah. I was afraid of that. We need to tell it to trigger on this only when it's stable for like 100 nanoseconds. Oh. Yeah. Okay. Greater than, call it 90 nanoseconds. Oh gosh, no. 90 nanoseconds. Oh, let's do quit making cute noises. when I backspace on the console, I'm getting a trigger on that 7FFO, just coincidentally. I might have to do segmented capture if this has too many false positives. Oops. Okay. Yeah, it's just a whole big mess. Maybe I can just do a time offset trigger from the serial. I might try to get some more captures of this, but maybe it'd be worth looking some more at the Grub source code before diving too much deeper into the scope. This might also be a place where it makes sense to switch from experimenting with the chain loader to loading a different thing. Yeah, this is unsurprising. So like it's not intentionally trying to go back into the BIOS or anything. It's just trying to jump to the beginning of the bootloader. It might be useful to know whether this happens before or after we actually transfer control to the boot sector. So far, all the boot sector stuff we've tried to do would have been calling back into the BIOS. Like either it's an operating system loader, and so we're loading additional disk blocks, or even the really simple debug things that I tried loading were like printing stuff to the screen using BIOS services. So maybe it's actually worth trying to chain load and or kernel load, whatever. Load something that definitely doesn't even slightly go back into the BIOS as a way of testing this. if it does even make it into the chain loader, or into the MBR we're trying to chain load, then the very beginning of the boot sector might also be a great place for like a scope trigger. Yeah, so what about a boot sector that just spams the serial port? That would just be a few bytes of code, and we could try chain loading to that from a file. We don't have to actually put it on the real MBR. And like before, I can test that it works in the emulator and then try it on the real machine. I don't actually want to keep using GNU ASM style. I'm going to convert this to NASM real quick. Oh. 3E8 plus 5. Alright, that should be fine. It needs a signature. Yay! You. So let's try booting without. Card. Okay. Camera. Sorry. Okay. That's interesting. Can we try that exact same test on the emulator? Do I want to read back the card image? Let's just put this in the build system. have serial debug and serial grub console. So serial grub console. Ooh. Oh, I accidentally entered the debug console. Okay. Right. Okay, that's a little confusing because it starts out still trying to display the menu over the serial terminal, but I can cancel the menu and now I have serial terminal on QEMU. Do we not have tab completion? Interesting. I'm just going to double check this, but I think we just discovered that the system as it's booting definitely doesn't make it into the MBR at all. Because one theory was that it was making it into the MBR, but then immediately failing somehow as it calls back into the BIOS to do things like read disk blocks or write to the screen. But this is a little fragment of code that does not depend on anything except for some registers and the serial port attached to ISA. So it can run pretty much anywhere and just spams the serial port with use. And it works in QEMU, but on the real system it fails right after that memcopy debugging we added. Yeah, just for consistency, I'm going to copy this exact same image since I built a new version anyway. I bet the problem's with the A20 re-enable. So Grub is trying to put the system back into its default 16-bit real mode configuration where memory above 1 megabyte doesn't exist. And there are a few different ways of toggling this compatibility setting called the A20 gate on a PC. And I've already noticed that one of those ways on this BIOS is broken. There's supposed to be a BIOS call you can make, and that seems to hang. And I discovered this when I was running that little toy OS thing, Metal Kit, on this a while ago. I had to change the way it was doing A20 gate. And it would make sense if that was happening now, because I mean, I only noticed that when it was flipping the A20 gate the other direction, going from kind of legacy mode to regular mode, but it should have the same problem in both directions. If that is the problem, though, I would expect that to only happen when we're booting something 16-bit. So maybe it's worth trying to boot something 32-bit and see if we fail at a different point. Let's try booting Linux and just see if the failure still looks at all the same. We haven't tried booting Linux since adding a bunch of this extra debugging. Cool. Yeah, like magic. That's convenient. Cool. Would that code work if I ran it in 32-bit mode? Probably not as it is, but I could compile something really similar to that with a multi-boot header and just run like a serial port spammer, but in 32-bit mode. Let's see, this is still the version of Grub that has that memcopy debug. Let's try that. Yeah. Ooh, post beeps. Let's stop that. Different failure. I mean, maybe. So I don't actually know how many mem copies there are. I should really turn on the rest of the debug to get more context. It might be different. It might not be. Yeah, a different failure. It might be worth looking at that one on the O-scope, because it looks like that failed in between two of the mem copies. I don't know what that means. We can trigger the scope on F to get this again. Yeah, I mean, there should be 3 of those sorted chunks. The first one looks like a no-op. That's interesting. Oh, maybe it is a no-op and it just generates no code. I should really patch this so that after all the mem copies are different, it prints a different character to the serial port. Yeah, that seems like a good assumption, that the mem copy probably is not the problem. So I wonder if this is also rebooting. I guess it couldn't hurt to look at it on the scope. I do need to do that with segmented capture so I get the whole thing. Seiko is like leaning up against the tripod leg. Ooh. We're getting at 80 really soon after these writes. Oh. Talkie boy. trade chairs? Okay. Kitty. Tuco, you're very pointy. I think the next thing to do once I can reach the keyboard again is look at the Linux loader and see if it's trying to mess with A20 or like generally what it does between the memcopy and the actual boot to see what this could be hitting there. Aw. trigger the scope on this. I think we need to add a few more triggers to this. Are we sure this is the 32-bit Linux loader? It really should be. Oh, hey, Tuco. Tuco, what are you doing over there? Don't, please. Hey. You wanna be over here? Hey, Tuco, don't. Mm-hmm. Tuke. Hey. Don't be chewing that. Do you want to do something that isn't chewing wires? I'm gonna go find a cat toy. I'll be right back. Oh wait, is this a cat toy? Tuco, didn't you have a feather ball in here? Tuco. Do you like either of these? Oh. Hey. Let's not be in those headphones, honey. Whoa. Can we share? You want me to open that? Maybe Tuco and me and the camera will all appreciate some cooler air. Alright, how does this boot? Linux parameters, blah blah blah. Okay, relocator 32. Looks like we're still putting the stack underneath the real mode bootloader, or at least where that would go, but I don't think that matters. Did I put that patch in common or ASM? I put it in ASM. I should put it in common. Oh, maybe I have to put it in both, because this does not include common. Oh, whatever. I don't need this to be clean. I'm just going to copy this code into the other file that I want it in. Just trying to debug this. So I want some pretty late output from both relocator 16 and relocator 32, and maybe some earlier output. So there's one step I'm maybe skipping between the relocator proper and the mem copies, and that's the there's a jump, but that's probably fine. If not, then I guess we'll narrow it down on this next step. How did we decide what the preamble was? Okay, that's for load address. Interesting. I also kind of have to re-explore what registers are okay for me to trash at this point. Reload GDT, disable paging. Are we relying on any registers here to stay alive? So as written, this trashes DI or EDI and AX. I'm gonna assume nobody uses DI here, just SI. And of course, I'm testing all this in the emulator. I should maybe try to explicitly, like, notate that I'm in the 16-bit version of this too. So I'll put a 6 there on the 16-bit version and a 2 on the 32-bit version maybe. second? What was the first? It's like the commenter describing a list of things they're doing to try clearing A20, but it starts with second. Oh, we're using port 80 as part of this A20 gate check. Oh. Interesting. Can't really do much past this point without messing up registers that should be set, but I think we can cheat a little bit and just mess up some registers we shouldn't, with the knowledge that the thing we're loading doesn't actually care. Let's give the 32-bit relocator a similar treatment, and then try this in the emulator. Hey, Tuco. Is this just a jump instruction? Yeah, the 32-bit relocator is much simpler. All right. Does any of that compile? Oh. Okay, so that should be present in the 16-bit and 32-bit sort of boot code paths now. We'll just have a bunch of characters coming out telling us which parts of this relocator code chunk it's actually visiting. And whatever turns out to be the latest kind of character milestone we get before the crash will hopefully narrow down the crash and also serve as something to trigger the O-scope on. I don't know whether to try the 16-bit or 32-bit relocator for this next. The 32-bit relocator is ultimately more interesting because that's how we get into Linux. It's also simpler. Let's do Go on back in. You wanted to take my chair. Wow. Oh, Tuco, what are you doing that for? Hey. We have reached the parallelizable part of the build. Alright, that's a compiled grub. Hugo. Let's see it go. There's a request for context. What am I trying to do to Grub anyway? I'm trying to make it boot. Just normal Grub things. Yeah, just booting regular old Grub and regular old Linux on a regular old 486 compatible voting machine motherboard. Okay, so there's our Grub. Let's get our emulated serial console. There's our emulated serial console. Got some weird line buffering going on here. Anyway, this is fine. Should we try 16-bit or 32-bit first? Let's try 16-bit. Setting up the chain loader and boot. Ah, okay, that's something. So all these Fs are from the mem copy in the relocator going forward, and then 6 is the 16-bit relocator starting, and it looks like we don't even get past the preamble. So now I'm wondering, is this a problem? I mean, this must be a problem with the debug code, because this normally works in the emulator. So something I'm doing here is causing it to crash. So what is actually going on here? The preamble is like a relocator, right? I mean, this whole thing is called the relocator, but I think the preamble is a thing that actually like rebases this chunk of code. Preamble. What is that Apple stuff there for? Oh, it looks like the preamble is doing an address calculation here that I probably messed up by putting something before it. Yeah. Let's maybe change this so that I'm putting all the code after the preamble. So I don't think I can have any space between the preamble and that label. If I'm just going to have two characters here, I'm just going to have them print 32 and 16. Yeah, this compile cycle is pretty annoying for making changes to the Grub source right now. Like I can just build like in the Grub tree. It's just really annoying to actually install that into the image after that point. And I'm also currently depending on having a 32-bit version of the Grub installer. There's a question about compiler caches. No, the problem is not just compilers. It's just a bunch of build steps. Like, look right here, we're cloning a Git repo. There's no reason for it to clone a Git repo. It's just that a bunch of logistics has to happen for it not to clone a Git repo. is one of those things where if I was planning on doing like development on Grub, I would have a different setup, but that's not what my setup is for. My setup is mostly for building a Linux image. Like, if I wanted to make this faster, I'd probably have to either set up a 32-bit cross-compile on my host machine outside Docker, or set up like a build inside Docker, but then either way I'd have to like patch in the Grub installer and then rebuild the bootloader. It's just annoying. There's other stuff I could do, like I could be applying my patches after the /configure and after one regular make. So I could just cache, maybe that's what I'll do if I have to do this again, is just have a Docker build step that doesn't have any patches applied and then rely on an incremental build after that to handle all the patches. Like, I'd still have to do a bunch of these steps again, but the most time-consuming part, I think, is doing the autoconf, automake stuff for Grub. And so that would skip all that. And then I'd still have to do all this stuff, because this is just packing in the disk image. And there's a comment that most of my time seems to be on the stuff around the compile and not the actual compile. Very, very much so. Like, the actual, like, parallelizable parts where we're just running GCC on a bunch of files take very little time. This machine has 20 logical cores. It's all just the fluff around the compile. Then there's another comment that cross-compiling is not such a big thing, actually. Yeah, I mean, of course, it's just another thing that you have to do. And then there's a commercial for something I've never heard of that's better than Docker, which doesn't work because I've never heard of the other thing. Oh well. Yeah. All right. Debug equals all. 16-bit again. Ooh. That made it all the way through. Cool. Let's try that again just to make sure I just didn't get lucky and it wasn't like a cosmic ray. But no, that looks fine. We should test the 16-bit and 32-bit modes. It's a little awkward to get into the console here. There we go. Oh, that's great. 1, 6, 2, 3, 4, 5, etc. all the way through K. always do this without reading any of these addresses. So protected mode target right at a megabyte. I'm assuming the relocator does not go at a megabyte in that case. Well, let's boot it. Oh, we got to 9. That was the whole thing too, right? Kernel panic, unable to mount root. So that's the kernel itself, which was a no-op. Then we had 2 other things. I don't know what either of them were, probably like parameter blocks. And I guess we don't have to relocate the relocator because we're not going into real mode. So that's great. And 9 was the last character here, right? Alright, I'm going to check this in, because this is a working experiment, and then we can run the experiment on the real computer. Okay, this commercial was apparently something based on gvisor. That's fun, I guess. Experiment. I'll be right back. Oops. Wow, such fast. Almost a whole megabyte per second. Alright. Card in the slot. Beep, 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 beep. Gosh, it's nice to be able to just throw the Grub console over to the serial port like that. Well, that's useful. 2, 3, 4, 5, 6 crash. So where is that? That's in the 16-bit relocator. Crash is trying to turn off PAE mode. Really? Really? Does that explain why this happens in 32-bit also? Let's see if that's also where we hit it in 32. Where is the PAE over here? PAE is between 5 and 6 on the 32-bit side. Interesting. Gosh. PAE mode. Okay. Right? Ah. So I'm going to make a patch that just disables PAE, and we'll see if that does anything. Or disables the switch for PAE here. Yeah, there's a question about what PAE mode is, if it's the thing that lets 32-bit machines address more than 4 gigs of memory. Yes. It stands for Physical Address Extension. Guys, it's been a long time since I had to mess with PAE, but if I remember right, it's like an optional additional layer of page tables that you can enable, so it changes how the system does protected mode memory resolution. Gosh. Okay, do I want to stack these patches? Let's just have a messy little source tree. Okay. Am I gonna actually make that change I said I was gonna do to make the build faster? Let me get that started while I'm getting the rest of this set up so that they can build at the same time. Docker file. I wonder if I already have these other ones in the cache. Okay, I should be able to get Docker started building that. So turning off PAE and the 32-bit and 64-bit relocators. Yeah, cool. This used the cache because I already had a version of that built. I should test this in QEMU and then on the real machine, just like I've been doing for consistency. The only difference in QEMU should be that it still boots, but we get different serial output because I changed one of the characters so that we'd be able to see that it's running the new code. Yay. I think last time I actually tried using Docker for much, I kept running out of disk space, but now I've got my Docker cache on a giant NVMe SSD. There's a question about whether PAE is a configuration option. Not in Grub, as far as I know. I mean, this code that I'm taking out was not conditionalized in any way. It was an option in a lot of operating systems and BIOSes because it was a CPU feature that you could choose to use or not use. Oops. It's too easy to accidentally open the debug stub. The debug stub is very chatty. Cool. Let's test 32-bit for consistency, but that looks right. There is some really annoying input buffering going on there. Yay. Cool. That's also the expected result. Let's copy this image to the actual thing. Very silly looking card reader I've got doing this. Oh, are we not focusing? Yeah, never mind. Tuco's more important. Let's just get this copy. Oh, there's a question about whether that was trying to enable or disable PAE. It's trying to disable it. I'm guessing that it's just writing to like a completely unimplemented bit or something. Like, probably what's going on is we caused a CPU fault and then like some kind of multiple fault, which then causes the machine to reboot. Like if you have faults while the fault handler is not actually dealing with it, then the CPU will eventually reset. And it looked like it was just fully resetting there, going right back into the BIOS via the reset vector. Pretty cool to actually be able to see the addresses coming out of the BIOS though, like watching the CPU pull the reset vector. Okay. Where's my serial debug? I don't think Minicom's running. Oh, did I lose my serial adapter? Oh yeah, I accidentally unplugged it. It was like right next to the card reader. Oops. Now connect the remote debugger, please. Okay. 16-bit? That worked. We just chain loaded Grub from Grub. on the real machine. Let's try Linux. PAE mode. That was not on my list of things that it was going to be. This isn't going to boot successfully without some more options, but this should get farther at least. Decompressing Linux. Oh my gosh. Unable to mount rootfs. Gosh, let's try just booting this normally. No more serial debug. Let's just give it a rootfs. I guess technically we just booted Linux, sort of. Oh, it would help if I plugged the power into the right socket instead of ground. Yeah, it takes it a sec to actually read the compressed kernel in. I have a shell. I-486, man. Authentic AMD. 31.9 bogomips. Yeah, no, this is a fresh kernel. This is 5.14.14 running on a AMD 486. Oh, what should we do next now that it runs? How much hard disk space do I even have free? Oh, I don't even have that much. I didn't even try to prune out Grub modules I wasn't using, but I've still got 40 megs free. Well, we could just have packages, right? Like, I have APK here, I just don't have a network connection. Gosh, can I fix this camera focus? Well, that's a pretty good stopping point, I guess. I don't know if there's something else I should try on this before wrapping it up, but that feels pretty successy. Run top. Look at all that free memory, 20 megs free. There's a comment that there's plenty to run Doom. Yeah, I already tried running Doom on DOS and it runs fine. It was running in a fairly small video mode. This display chip does support hardware stretching of VGA modes. It's just not enabled currently. So you're seeing it stretch the text mode, but if I was to switch it into a VGA graphics mode, it would be doing like a pixel accurate thing instead of a stretching thing. There's a question, how much memory do I have? It's 32 megs. 32 megs of, what is this, EDO DRAM? Yeah, gosh, what else is there? This is Alpine Linux with a 5.14.14 kernel. Does this not know how to do APK version without downloading things? Cool. Gosh, I'm gonna pet the cat for a minute. Let's do this one. That's just satisfying. There's a lot of interesting stuff we could do on here now that we have Linux, right? We could actually try to get the graphics acceleration working, which was going to be my main thing to focus on, really. I figured getting Linux to boot wouldn't be a big deal, and I'd be mostly fussing with X11. It seems like we could probably use the PC card slots. I don't really have any cards to put in them, but maybe if I find a good deal on eBay or something, we could try giving this thing Ethernet. Yeah, victorious cat petting. I think that's a good idea. Have a little bit of cat petting victory. So, like, what have we actually got working here? We've got a basic Linux kernel. We've got the watchdog timer turned off. We can boot. We have 64 megs of storage, or 64 megs of flash and 32 megs of DRAM. Oh, touch driver. You're right. I actually have a touch driver. Can we try that? Gosh. Where would this be? There's no proc input, right? It's like a sysfs thing. Oh, we could check dmessage. Do I have less? Gosh, that focus is annoying. So yeah, we have one parallel port and 3 serial ports. TTY-S0 should be our touchscreen. TTY-S2 is where our debug console is now. Oh, I should see if I can just say hi to my serial port. No? That should be the right port. Oh, basebaud. Yeah, I don't know if that's actually still set up. Do I have STTY? I do. Oh, is that right? Cool, so I could theoretically transfer files and not have to rebuild my compact flash card every time I want to send some stuff. That might be handy. Yeah, I was gonna look for input stuff in either proc or sysfs. We could also just look in dev. Although I don't have udev, so like presence or absence of things in /dev doesn't really mean much right now. And we also probably have a dev input for the AT keyboard. Like, one of those is probably the keyboard, one of them might be the touchscreen. Can I not control C? That might be a problem. I don't actually have my TTY set up for that. I don't have any proper TTY set up at the moment. I might have to reboot. Oh gosh, did Control-Alt-Delete just work? I've never seen Control-Alt-Delete work successfully on this machine. I wonder if Linux changed some config that fixed it. That's handy. This is almost like a real computer. Yeah, I mean, we could give it an IP address with PPP or whatever. I mean, it does all the regular computer things now, basically. Okay, what were we doing besides messing with serial ports? Touchscreen. It is pretty trippy seeing sysfs on a 486, right? Oh no, I did something slow. Oh, is that it? Devices. Right. Sys devices platform I8042 serial IO0. Input 0. Oh, that's the AT keyboard. Right, serial IO0 is not the serial port. That is the serial I/O interface on the 8042 keyboard controller chip. We didn't see anything in dmessage about the touchpad, right? What was it called? It was called DynaTouch, right? Yeah, I suspect that driver needs some command line options to tell it how to load, because like I didn't give it any options. It would have no reason to assume TTY0, right? So I assume I need to configure that. I wasn't really expecting the touchscreen to work just right away. I guess we could just like check whether we're getting serial data though. Do we have a hex dump? We do. We could do STTY. What was it? 2400 baud. It's not immediately work, but that doesn't really mean much. There could be a bunch of reasons for that. There's a question about whether it's treating the touchscreen as a mouse. I don't know what the Linux driver does. I assume it's just a regular input subsystem absolute pointing device. The hardware it's a device called the 3M DynaTouch, and it was an OEM part. So there's just like a PIC micro with a custom firmware on here that implements it. It's got like a basic serial protocol. It just like sends 3 bytes per packet, and it has an X and a Y location and some flags. It's also got a configuration protocol where you can store stuff in EEPROM, and we messed around with that from DOS a little while ago. So yeah, there very well might be some tooling and or some yak shaving to do to get the touchscreen working, but it seems possible. Don't have LSPCI here. It's not exactly an LSISA. Yeah, we don't have any buses that can tell you what's on them. I don't have Vim. I have VI. Oh, we should try writing to the disk. Read-only file system. Oh, is it gonna do a clean reboot and everything? I just press Control-Alt-Delete. Let's see if it actually unmounts. It seems to be hung though. Maybe I'll have to power cycle it. Oh yeah, it would be cool if Linux supported the soft power option. Like right now there isn't actually a way to turn it off cleanly. There's a comment about ACPI. This is way before ACPI. This is also before APM. I mean, APM existed, but this doesn't implement APM. I should install some swag like Figlet and CMatrix and Cowsay. Yeah, so I have a little compact flash card that I can read and write. Cool. Well, I could install packages on the CP or on the PC side. But anyway, I think this is a good point to wrap it up. I don't want to go too far into the weeds here with just playing with a Linux system. I'll think of some good things to actually focus on, and then start this properly on the next stream. Oh, hey Alexis, welcome to the chat. Yeah, so I'm about ready to wrap this up, but just for a little recap, I started this stream doing, with the intent to do some debugging on Grub that went a little deeper than we were able to do with GDB. So the last stream was GDB debug stub for Grub, but it was hitting a crash that I couldn't figure out where, while the relocator in Grub was trying to write to some low memory, it would end up crashing. And I wasn't sure what that was. I couldn't find any link between that memory and stuff that should have been vital for the debug stub or for any other parts of the OS that we're still using. But I'm assuming at this point that that's what was going on, that there was something going on there, either something I didn't notice about, like, you know, maybe like one of the descriptor tables for x86, or maybe something that, I don't know, I ruled out a bunch of things, right? Like it isn't actually the GDB stub itself, it isn't the stub's interrupt vector table, it isn't the original interrupt vector table, it isn't the IDT as far as I can tell. So yeah, it ruled out a bunch of things, but it was still crashing. But importantly, I was able to reproduce that crash exactly in QEMU, which proves that it's not due to this weird hardware. So kind of put that aside and switch tactics to, instead of using GDB, to patch Grub to do some low-level serial port debugging. So it would just spam a character out to the serial port when it reaches a particular point in the relocator. Did a bunch of that, and then ran that in QEMU to make sure the test was good, and then ran it in the real hardware and watched it crash right as it was flipping the PAE disable bit in the processor. So I still don't know why that makes it crash, but I'm assuming that's just not implemented on this processor, and something that's going on causes it to do like a triple fault right there, and it ends up just rebooting the whole machine and going back into BIOS, and then probably failing to post half the time. So this is a patched version of GDB. It's got that debug patch in it still, but I'll probably remove that because it's not necessary anymore. The important part is that I patched it so that in the 16-bit and 32-bit relocators, it's no longer disabling PAE mode. So yeah, that seems to fix it. I wonder if anybody's ever run Grub on this particular CPU. This is not an Intel 486, this is an AMD 486. Specifically, it's an embedded AMD 486, so it's a slightly weird core. Oh, this little guy is so peaceful. Well, thanks for hanging out, everybody, and a special thanks to everyone who contributes on the Patreon or tells their friends about the stream, or just folks who show up and hang out. It's nice to do this regularly, and I'll try to keep up this daily schedule here. Duco seems to be okay with it. He's really digging this red chair. Well, happy hacking, folks. I'll see you tomorrow.